Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Today's episode is brought to you by our sponsor, Arteris. We're going to be talking about on-chip interconnect here on the show today. SoC designs are getting bigger and more complicated, with more and more AI content on each chip. This all makes connecting those blocks together with a network on chip really hard, and with NoCs, network on chips, representing around 15% of silicon area, it's crucial to get it right. In this episode, I'll be talking with Michal Siwinski, Chief Marketing Officer at Arteris. Arteris' network on chip IP technology is called FlexGen, and Michal's going to talk us through what that is, why it's needed for modern SoC design, and why NoC design is going to become an even more critical part of chip design as SoC designs continue to grow. Here's my conversation with Michal. Michal, welcome to the show.
Pleasure to be here.
So for what we're going to talk about today, I think we'll start with maybe set the scene a tiny bit, because the background to this is SoC designs are getting bigger and bigger and getting more and more complex, and we're adding AI basically just about everywhere now. What does this mean for on-chip interconnects? Let's maybe talk a little bit about the new challenges for on-chip interconnect, and why does having more AI content in particular on the chip make interconnect a harder problem?
Yeah, that's a great question. So, there's a couple of basic things going on, which is, of course, as we add more content of any kind, as chip gets bigger and more complex, which is the trend for the last, 50 years, 40 years, it's been accelerating though, right? As things get more complex and larger, the actual complexity of having all that data travel around the actual chip, so the actual compute happens, it's been getting more complex for a while. However, AI actually changes that dynamic even further. So what's been happening is that with, of course, the great injection of a lot of the AI software, the underlying computing has been evolving and evolving rapidly. It's happening not only in the data center, but it's also happening at the edge. And the implication of that basically means you're adding a lot more logic that actually is extremely data intensive. So you now have a lot more data that needs to travel within specific subsystems and across the whole chiplet or SoC. And all of that needs to be properly interconnected because, again, the data is the fundamental thing that is actually getting computed. So from the interconnect, that basically has been almost a shift from a evolutionary challenge to a revolutionary challenge, where you're now dealing with a complete step up in compute requirements that need to be dealt with.
One of the key things here is the introduction of the network on chip, right? I know you're going to tell us a little bit about network on chip and what it is. Why do we need a network on chip overall?
Yeah, of course. So, one example I like to give sometimes is that think of the days of the traditional telephone, right? So people used to have, direct line connecting from house to house. You can see those nice pictures from turn of the last century, right? And then all of a sudden people invented switchboards, and that was an improvement. That's kind of like equivalent of bridges on buses on chips, right? And then we basically, moved into the whole area of interconnect and networking, right? The internet and networking. So think of, Cisco, like that kind of routing. So that was the network concept. So this is basically taking that same notion that as you have a lot more data and a lot of connection points, you need to be routing them in a very smart way. And so that's where the concept of network on chips comes from. It's been about, it's about 20-year-old concept. Arteris, we're pioneered this technology, but it's basically kind of at the center of how you actually have very efficient data movement across the, vast amount of silicon that it has to traverse.
Yeah. How critical is it to get this NoC design right? Obviously, yes, every SoC design is different. How important is it to make sure the NoC is absolutely optimal?
Well, yeah. So, it's if you're trying to get from point A to point B, you're trying to go from here to your vacation, there's no road, no highway, no airplane, no boat, no nothing, right? It's challenging. So same thing applies here, right? You really need data to be actually effectively going from the CPU to GPU, memory, NPU, TPU, whatever kind of XPU you're using, right? Plus all the peripherals, plus all of the caches and everything else. So that data movement is actually the core of what you're actually doing when you're actually doing computing, right? I mean, yes, the XPUs will do, let's say, multiplications or other things, but that data then gets multiplied and then it traverses somewhere else to be multiplied again or change again. So, I mean, this kind of like actually the data connectivity, data layer is actually extremely critical, because if you don't have that, you don't have performance, you blow up your power, you actually cannot even complete the designs to spec. So it's becoming very, very critical, particularly in the last few years, because the scale of designs, particularly with AI, is actually just making it that much more a necessity. Versus before, it was a great thing to have. Now it becomes a necessary thing to have.
How many NoCs would you find on the biggest chips then? I mean, the more NoCs, the more critical the NoC design is, right?
Well, yeah. So that's the funny thing. People sometimes think that, oh, well, I have one NoC, one kind of way to connect things. And yes, some people are still traditionalists and build one big gigantic NoC for design. However, in reality, most of the people think of it the same way they would do with subsystems of any kind of a chip, right? So typically, any subsystem will have its dedicated NoC. Some will have multiple because of different things they subconnect. And so, on average, you'll see a chip having anywhere between, 5 to 20 different unique NoCs on it. Some designs pushing the envelopes. I mean, I've seen NoCs where there are 30 instances. I heard of even more instances, which is kind of interesting, but on its own. But fundamentally, you're talking about dozens, kind of NoCs that are unique that you have to do, with each one being a different level of connectivity. And basically, in totality, that basically accounts for about 15% of silicon area, no matter what application you're creating, whether that's a data center chip or a very area optimized, sensitive edge device. It's basically the average, no matter what, is about 15%.
At 15% of silicon area, this is the design of this network then is going to be fairly critical to PPA overall, right?
Exactly. So this is actually one of the key things, right? So PPA in general, and specifically, if you actually double click, it actually comes down to the wires, right?
Yeah.
So the wire length specifically is a challenge because it correlates obviously to area and power. But as we see these amazing new designs in advanced nodes, anytime you're going at 7 nanometers and below, and nowadays, right, we're talking 3 nanometers, 2 nanometers, or 5 for some mainstream designs, right? At those geometries, it is all about the wire length, and the wires will actually be the biggest problems when people are trying to convert on the back end of a design. And so being able to optimize that wire length and dealing with it effectively, which is also where the architecture of network and chip comes in, that actually becoming very, very critical.
Okay, tell us a little bit about FlexGen then. Given that each NoC network is going to be different, FlexGen, the tool we're going to use to design this NoC, to what extent is it hardware IP? To what extent is it a tool? Or it's some combination of both, right?
FlexGen is our smart NoC IP technology. And like any other IP that has a lot of different potential connection points, the flexibility around it is absolutely essential, right? In a way, hence the flex in the name. But in general, what that basically means is that, of course, it is IP. It has, it has basic building blocks for all of the right transformation of data and for everything to get connected, all the switches and everything else. But at the same time, how you actually instantiate it, how you actually configure it for each of the unique needs of each connectivity point, it's actually different. So from that point of view, there is obviously a layer of automation on top of the IP itself that actually allows this not only configurability and parameterization and so forth, but actually adding the layer of smart heuristics to actually move from just having great IP that is highly configurable to having IP that actually is smart in the way that it's doing and providing this flexibility where you can go kind of anywhere from pressing the equivalent easy button, hey, figure that out for me, down to basically being an AI agent, which is basically trying to provide advice to an expert user in terms of them optimizing what they need to optimize.
Wow. Okay. So the main technical innovations then behind FlexGen would include AI, right?
Yeah, so the underlying technology, of course, as always, all technologies nowadays are trying to tap into AI, right?
Yep.
And rightfully so. At the end of the day, AI, people think that AI is this sometimes mystical thing. It's not, it's just math, right?
Mm-hmm.
At the end of the day, there's a different heuristic approach to solve difficult mathematical problems. And in that regard, FlexGen is utilizing the same notions at being able to actually add in that smartness into how you need to do the computation to figure out the best IP gets created for the best power performance and area dimensions. And it basically becomes, hey, how can you find the right local minima? If you think about how AI actually is computing things, right? That will actually give you the best optimization, but at the same time, make it in such a way that you have a high degree of determinism, which is actually a little bit hard sometimes in AI kind of augmentation of technology. Because when you're building something, you want to basically make sure you can take an incremental approach sometimes, right? An engineer, an architect will definitely decide that something needs to be done a certain way, but then they might want to tweak it. So incrementality and determinism are obviously, key aspects here, which we're kind of proud of, because a lot of the, initial AI technologies out there, sometimes where, well, you run at different times, you get different results, and that's great, but that's actually not at all the right way to design a chip, right? That's not how people do this.
Yeah, I guess you want to believe that there is only one optimum when it comes to power, performance, and area. We're optimizing all three of those in an automated way. You want to believe there's only one solution, right?
Right. And of course, there's going to be probably several in reality, and obviously where your starting point still matters. But as you incrementally improve it, you want to make sure you actually try to get to something that is going to be converging, because convergence for timing, for the backend, right? Can you actually do the right PPA so that you backend convergence with closing timing when you go to the backend tools? Will that work? That's the physical awareness concept that is also, in FlexGen technology. And then the same thing on the, on the front end, when you actually try to figure out the right topology for the right architecture of this connectivity, will it actually converge, and will it actually converge without blowing up your power performance on area, right? So that's bringing all of that together. It's kind of cool technology.
To what extent do you still need to be an expert into chip interconnect to use this tool? Like, can I do it, or you still need to be an engineer, right?
Well, I think if you're not an engineer, you probably would not necessarily be working on this kind of stuff to begin with.
You're not trying to replace people's jobs with this.
No,
right?
no, not at all. So in reality, there's a couple of basic things. So one is, of course, that fundamentally, even putting this technology aside, right? Most companies actually have a critical shortage of people that actually even know how to build connectivity across designs. The biggest, most advanced companies, you have a handful of architects, but the architects are not actually, they may be designing some ideas, but they're not actually the ones that are building these networks, right? So you have a handful of specialists that actually understand architecture, understand data flow, need to understand the back end. So even if all of these engineers were to be, multiplied by 5 or by 10, there's still a critical shortage. So the first issue is there's just not enough expertise to even do this. And now compounded by, let's say, an SoC having a dozen different NoCs. So first of all, these resources are completely stretched or not existent. So part of this is, of course, if any engineer, if she or he is working on anything that is specifically hard, can we make FlexGen make their job a little bit easier, but at the very least, improve the underlying productivity of it, just shorten the process to get it done, right? And in a way, we actually started this technology focusing on productivity because of that engineering shortage. And so that somebody can actually get their job done faster. And on the other extreme, for maybe a subsystem where the NoC there is maybe less critical, maybe you don't need to worry about high performance for, let's say, your low-end peripherals, right? You should be able to just basically press the button and the NoC gets generated, and having that continuity between one and the other. Because again, there's just not enough people that can do this stuff. And as designs are exploding, this is becoming a huge bottleneck. And actually, the NoC design and its interaction with the backend timing closure is often on the critical path of an SoC.
Can you tell us anything about how you make it deterministic or how you ensure it's deterministic? Because obviously AI is known for more random type of results, like you were saying before, but I'm curious about how that works.
Yeah, so at the end of the day, it's kind of how we've created it, and there are certain AI capabilities that we are exploring to add over time. That potentially we might add some non-determinism later on for some additional corner case exploration. But right now, we try to make sure that we're very much taking in the approach of think of it more like as a curve fitting. Being able to actually that if you're already optimizing something, can you basically continue to tweak it and optimize and think of how things can be moving around a little bit, and as you're building out the network, so you can actually get something that's more predictable. So there is, some kinds of fundamentally machine learning technology that we're leading into, and some other things that right now we we might get into it later if it's relevant. But, at the end of the day, the AI technology there's so many different approaches and there's some different ways to do it. It's actually quite broad. So at the end of the day, from our point of view, we're just trying to make sure that we actually can provide slightly more automation that is smarter. And that's kind of interesting in a way that not only are we actually seeing this being a lot, being able to create a process that's a lot faster and works a lot easier for engineers to be able to create these connectivity for design, but also that they're actually getting very nice gains in the underlying power reductions through the wire length. And it's kind of a combination of the two that actually is going to be kind of more pertinent. People actually are using this technology, and that's where, do we explore some other corner cases over time? We'll see. Where there's a lot more technology that we're working on.
Yeah, absolutely. Okay, tell us a little bit about FlexGen and where it actually applies. I think people who listen to this podcast are either users of AI chips or they're building AI chips. But to be clear, a NoC on the chip is going to be between different blocks on an SoC. This isn't within an AI accelerator block itself, right?
Well, it could be actually. It depends, right? So fundamentally, this NoC technology, if you kind of take the approach again that the network on chip is basically connecting any endpoint of any logic or any logical function that you're doing, right? It could be applicable to any kind of a design in general, right? And particularly anything where you have either performance and concerns or fundamentally you're just computing a lot of data, right? So would this be applicable? You're building a tiny little edge sensor that maybe has some MEMS. And you're doing it at 45 nanometer technology, probably not. You don't need to worry about a lot of data. But anything that is AI in nature, anything that is vision in nature, or anything that is just advanced, right? Absolutely will use this kind of technology. And this is where kind of again to the point that the inclusion of machine learning compute into any kind of application, that's increasing, right? So within the, if you look at a specific accelerator, whether that be a subsystem or whether somebody just had an NPU that's, that's built in as part of the chip or as a separate chiplet, you first of all, can you connect it effectively with FlexGen? Yes, of course, right? But it's not just about how that one network for that accelerator or for that machine learning piece will need to be connected by itself, but also then how it interacts with the rest of the NoCs within the chip. Because at the end of the day, these are not separate islands that don't talk to each other. All of them actually need to talk to each other. So you actually have to synchronize the data traffic across all of these different subsystems within any kind of design, whether it be a complex piece of IP you're building, whether it be a chiplet, whether this be actually a custom ASIC, an SoC, or an FPGA, right? FPGAs, for example, are also utilized for AI accelerators, right? And we see a lot of usage of our technology in those applications as well.
Oh, perfect. What about if it's a multi-die, big multi-chiplet design? A lot of big AI accelerators now are multi-die. Can you handle that as well?
Yeah, so that's something that we handle with combination of both what we do and also working very closely with our third-party ecosystem players on the PHY side, on the physical layer. Mm-hmm. But from a underlying fundamental data connectivity point of view, we certainly can, and we have lots of customers that are designing chiplets already and have been doing it for years or in some cases over a decade, where they're actually making sure that the underlying data connectivity between the networks, whether it be on one chip, one die, or multiple dies, right? So multiple chiplets, right? That data can be synchronized. So on the protocol layer and the data layer, right? We make sure that we actually support that, and that has been, and it's silicon proven. It's multiple products out there have this kind of stuff. But obviously, we're trying to, right now. We don't necessarily go into the physical layer. So this is where we would work with a Synopsys or Cadence or Rambus, or pick your PHY supplier of choice, who optimize actually the physical connection, and we make sure that we have the right controller level integrations and connectivity.
So I know you have an example for us about where FlexGen made a real impact on an AI chip design. Tell us about that.
Yeah, sure. So there is, so one of the early adopter customers that we're working with was actually kind enough to share some of the data for, kind of public leverage. And, it was an interesting comparison because they were actually a power user. They actually are very, very expert users of NoC technology in general. And they certainly create, very advanced designs to begin with. So this is kind of the let's say the most limiting comparison, where you have the smartest possible expert user. Can you basically make their job easier and better, right? So, of course, we wanted to make sure that things happen faster, and they reported that absolutely they were able to move the task from what was weeks down to hours or days. And that was nice, but actually the more interesting things came over that the maximum latency in their specific design got reduced by about 51% by the way they measure it. Overall latency was also down.
51% is a massive decrease in latency. That's crazy.
It is. And, and some of that came over because actually, the FlexGen technology was able to revisit some underlying assumptions. So you can kind of think about, kind of back to, AI compute, right? A lot of the time, one of the limitations of AI is actually human bias, right? Sometimes AI does a better job, AI heuristics do a better job if you actually start with a slightly less constrained environment and then you add constraint, versus if you pre-bias any kind of AI heuristics, sometimes you're going down too far a path. So the way our technology is built is actually such a way that in this instance, there was a before and after view of, what do they do with, our FlexNoC technology prior to FlexGen, and the assumptions they made on that design, and the next generation of that design that was kind of similar. And they were making similar assumptions about the data connectivity and data flow, yet FlexGen was actually able to find a different way of doing it that was actually much more optimal, right? So this is kind of the notion of, again, letting the technology use its smarts to potentially explore alternative ways to solve the problem that might turn out to be more efficient, right? And in that case, yes, 51% maximum latency reduction, obviously huge. But back to the point of also advanced nodes, in that specific case, the overall wire length went down by 26%, right? And in longest wires by about 30%. So, and that actually made a huge difference when they're actually thinking about how they're actually going to, take this to silicon and scale. And this specific instance was an ADAS, so autonomous driving a chip, right? So mixture of AI, mixture of safety, mixture of ARM, RISC, and different APUs kind of technology. So this
worst case scenario, AI and safety on the same chip, right?
As gnarly as you can get, done by an expert, and can you make it better, right? So because of examples like that, right, I'm actually pretty confident that for anybody who is this advanced, they will be able to get great results. But conversely, anybody who is potentially still ramping up and or is focusing on one specific subsystem that is critical, and then the other 15 is like, well, crap, I'll get to it over the weekend, and can the thing help me, right?
Yeah.
Time is at a premium. People like the weekends.
People do like their weekends. Tell us about what's coming next for FlexGen and for Arteris as a whole. What are you working on next?
the FlexGen technology to begin with, there is a lot more stuff that we can still, of course, do with various AI support of technology. And that means two different types. So, adding more capabilities as we continue to optimize our technology for the growing complexity of AI designs that our customers are creating. So that's first and foremost most important. It's nice how you can actually see that in the last few years, because of how since CNNs came online, right, the machine learning software stack has been evolving so much that the underlying compute change rate has also been accelerating, right? So, we kind of think about, the Moore's law, complexity doubles every 2 years kind of a thing, right? And compute doubles, right? Now, really for the last decade, and it was kind of research, few cases here and there, but now it's more commercial. We're basically moving the AI compute is basically doubling every 3 or 4 months, right? If you actually think about how that's evolving. So that means that, and a lot of it is, of course, in the software layer, but that also has huge implication, the underlying hardware. So the way people are approaching, tomorrow's, data center design and edge devices of any kind, right? The underlying compute of that is increasing and shape and evolving quite a lot. That means, the simple way to think about it is, as you have more parameters, as you're doing more advanced models. So people move from, a GPT-3 to 3.5 to 4.0, using that example, right? The number of parameters basically moves from billions to trillions. The implication on that on the hardware is that the actual data lanes need to get much, much wider to even just be able to compute that. So things are getting wider, which means, more wires in the buses get bigger, and they still have to be switched and, right? The power performance complexity doesn't change. People also need to deal with the power envelope. So everybody's trying to go into the latest, more advanced node, right? Yep. So of course, everybody's excited about, doing things in 2 nanometers, 18 Armstrong, 16 Armstrong, 14 Armstrongs, right? Which is amazing. And that's going to be great for power consumption, energy usage. But that also means that how you design that and the pressure on the wires again, so network on chip again, is going to be paramount. So there are certain things. We have some, key lighthouse customers that are guiding us and telling us what the problems are going to be, not just, this year, next year, but 3 years down the line, 5 years down the line. We're obviously making sure that we're innovating this technology ahead, so we're ready for all those challenges. And conversely, using AI in our technology, again, there's more AI stuff that we can add to make the smart even smarter. So we'll continue doing in both directions. Dealing with AI is fun. Customers designing all of these AI chips is just a blast, right? So I think this is something that's going to keep on continue to be an interesting challenge. Tech is never boring, although I would say, there was a period, a decade or so ago where kind of semiconductors were getting a little bit boring.
A bit mature. Everything matured a little bit. Yeah, not boring. Come on.
Well, it's exciting. It's extremely exciting again. Maybe too exciting.
What a time to be alive,
but I don't think that's going to stop anytime soon, right?
Yeah.
So I think that will continue.
Sounds great. Thank you very much, Michal.
Thank you.
Thank you very much, Michal Siwinski, for the thoughtful conversation around FlexGen. This episode of AI with Sally was brought to you by Arteris, and thank you very much, Arteris, for sponsoring us. If you want to learn more about Arteris or FlexGen, please check the links on the podcast page at eetimes.com. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspencore Media. The host is Sally Ward-Foxton, our project manager is Colleen Heckman, and the producer is James Eade. Thank you for listening.